This is the Electro Sketch's final progress report. My name is Tyler Rossesell, and I'm an electrical engineer here at OSU.
My name is Henry Middles, and I'm also an electrical engineer at Oregon State.
My name is Wei Chun Shen. I'm also an electrical engineer at OSU. We'll begin by giving a system overview of our project, and then we're going to give a rundown on what we accomplished throughout each month through our timeline. And in our block diagrams, we'll be going through the mobile application block, the processor block, the motor control board block, and the enclosure/power supply block. Lastly, we're going to go through some of the challenges that we faced, as well as addressing some of the future improvements that can be made.
The purpose of our project was to create a portable, handheld laser light show that could be used while camping or for other outdoor activities. The goals we had for the project were to be able to display basic shapes, be able to control the system wirelessly, have it be able to withstand vibrations and small drops, as well as it being battery operated. Some of the features that we included were it being water and dust resistant, as well as several animations including spinning and bouncing.
Our timeline for the project started off in October through November with research into the theory of operation as well as the best use for redirecting a laser. November through December, we started coding along with constructions of individual blocks. Late December through January, we started with proof of concept of the device and making adjustments to our blocks, as well as having our first individual block checkoffs. January through March, we finalized the initial prototyping as well as debugging any hardware and software codes, as well as having an all block checkoff. March through April, we had our first system checkoff, as well as entered the final stages of prototyping our device. April through June, we had our final system checkoff, along with the Undergraduate Engineering Expo, and any additional changes to the system that we saw fit.
Here's an overview of the block diagram. Wei Chun was responsible for the mobile application. I was responsible for the processor/code section. Tyler was responsible for the motor controller, and the three of us collaborated to complete the remaining blocks.
For the mobile application block, the app was built using a program called Android Studio, which used a language called JavaScript. In that, I was able to build a GUI interface for the users, and the users will have the ability to choose the image from their phone storage and upload the image in bitmap format. Those things can be done through wireless connection protocol called forward transfer protocol. And we also use a router to set up a static IP address for more secure and consistent connection.
The processor and code blocks consist of a digital to analog converter, or DAC, with associated level shifting, as well as a C++ program running on a Raspberry Pi. The code reads in bitmap files, saves the X and Y positions of each pixel to a linked list, then runs those points through a path planning algorithm to sort the data and determine the laser's path. The new points are modified to account for any animations, and button inputs are checked before the data is sent to the DAC via SPI. The analog output from the DAC then goes to the motor control boards.
The motor control block consists of an X and Y galvanometer driven by an X and Y motor control board. The motor control boards take in a digital step signal from the processor, compare that with the current position of the galvanometers to create a velocity signal which is sent to the galvanometers, which cause the mirrors to accelerate in the desired direction. The galvanometers use a IR optic feedback system to give the current position to the motor control boards.
For the final block, we have the enclosure, the pre-selectable buttons, and the power supply. The power supply uses a reed switch to power on and power off the system. The systems will be supplied using two batteries, one 5000 and one 2500 milliamp LiPo battery, each rated at 11.1 volt. The motor control board will be powered by two sets of boost converters rated at plus and minus 20 volts, and the processor will be powered by two buck converters, each rated at plus and minus 5 volts. As for the enclosures, the buttons, and the USB port, those parts are IP67 rated, which can be water resistant and dust resistant.
This is the Electro sketch demo. So what we're going to do in this is we're going to turn on the system, use the mobile application to upload an image, cycle through the image with the pre-selectable buttons, and view some of the animations. Here's the system being turned on with a magnetic reed switch. And we'll be back with you as soon as the system has fully booted on. So, now that the system has fully booted on, we'll have Jim come up here and explain how to use the mobile application to upload an image.
Now I'm going to demonstrate how the mobile app works. Here's the mobile app. You click on it. Here's the choose buttons that you can choose a bitmap image to upload. Once you select an image, you can then hit a upload button, and the image will then be sent wirelessly to the system.
Now that an image is stored on the Raspberry Pi on the system, we can cycle through it with the cycle button here. Now you can see we're displaying an OSU. There's also several different animations that the system is capable of, including spin and bounce. Next, we're going to show you how to shut the system off.
And now we'll demonstrate shutting down the system. So we'll do this by holding this button back here for 3 seconds until the Raspberry Pi turns off. We can tell the Raspberry Pi is off when the laser goes off. And now we'll use our dongle to shut the system off. And in 20 seconds, the system will have fully shut down. And as you can see, the system has come fully off. Thank you for watching our demonstration.
Some of the challenges that we faced during this project were budget constraint, particularly during the prototyping phases, as well as the PCB shipment mishap, along with several high-cost items such as the enclosure and galvanometers. Additionally, the group members came in with limited knowledge of how the system works. Mostly in each individual block, group members had to invest heavily in basic aspects of their blocks, such as how a mobile app was made, how to code a pathfinding algorithm, as well as designing an analog motor control board. Finally, the last challenge we faced was the power supply requirement, which required our system to run for 8 hours, but due to the system's high current draw, we were unable to meet that, as well as creating 20 volts from two 11.1 volt batteries.
One improvement that we would like to make to our system is the quality of the final image. This could be done by better tuning the motor control boards in addition to speeding up the code. We would also like to add more complex animations, like having the images scale with sound or music. The last improvement would be the battery life, which we would like to get to 8 hours. This would require better power management, a more efficient laser, and a larger battery.
In conclusion, we were able to pass 9 out of 10 of our engineering requirements for our project. The only one that did not pass was the battery run test, which we fall short on the 8-hour mark. But overall, it's a great learning experience building a laser projector, and we like to use this opportunity to thank our stakeholder, Don, for his guidance and his support. Thank you.
Thank you.
Thank you.